Welcome to This Explainer. Today we're diving headfirst into something totally fascinating and, honestly, a little violent. We're talking about the physics of hydraulic jumps. We're going to uncover exactly how engineers purposefully harness these chaotic fluid phenomena to tame literally millions of watts of kinetic energy before it can destroy our modern infrastructure.
Here is our roadmap for today. 1. The high-velocity water threat. 2. Physics of flow regimes. 3. The hydraulic jump phenomenon. 4. Calculating conjugate depths. 5. Engineering the stilling basin. And 6. Taming megawatts of power.
So let's kick things off with a pretty critical question. What exactly happens to millions of watts of kinetic energy at the bottom of a dam? Think about the immense stakes here. You've got this massive volume of high-velocity water rushing down a steep concrete spillway. Where does all that energy actually go? If this were a bomb, we'd evacuate the area, right? But dams absorb this kind of explosive impact every single day.
All right, Section 1, the high-velocity water threat.
We really have to understand the pure destructive potential of uncontrolled, fast-moving water before we can appreciate how engineers actually stop it. When water exits a spillway, it enters a state called supercritical flow. This flow is incredibly fast, it's shallow, and it carries an extreme amount of kinetic energy. If this torrential, gravity-driven water is just left unchecked to hit a natural riverbed, it won't just flow peacefully away. No way. It will instantly gouge a massive scour hole right into the earth, essentially eroding the foundation and collapsing the very infrastructure that released it.
Moving on to Section 2, Physics of Flow Regimes.
To neutralize this massive threat, we have to open up the invisible toolkit of open-channel flow physics. And the single most important concept we need to grasp here is the Froude number. It's a dimensionless parameter that represents the ratio of inertial forces, basically the water's forward momentum, to gravitational forces. Think of the Froude number as the ultimate indicator, or kind of a master key, for predicting exactly how a body of water is going to behave in an open channel.
This beautifully illustrates the contrast between the two extreme states of water. On one side, we have subcritical flow, where the Froude number is less than 1. This is your slow, deep, tranquil water. If you drop a pebble in it, the ripples can easily travel upstream against the current. But on the flip side, we have supercritical flow, with a Froude number greater than 1. This state is so dominantly fast that physical information, like a wave, literally cannot travel upstream. The waves are swept instantly downstream. In this state, the water behaves much like a supersonic shock wave, entirely dominated by its own inertia.
Which brings us to Section 3, the hydraulic jump phenomenon.
So what exactly happens when that supersonic-like supercritical water inevitably slams into a tranquil, subcritical body of water downstream? Well, you get a hydraulic jump. Because the fast water can't send a pressure wave ahead to warn the slow water, it just violently crashes into it. The result is a sudden, stationary, and incredibly aggressive roller. It acts as a massive mechanical brake on the fluid, instantly converting all that dangerous kinetic energy into large-scale turbulent eddies, aeration, and eventually microscopic heat and sound. It's an absolutely stunning display of fluid mechanics in action.
Now, the crucial point to understand here is the difference between alternate depths and conjugate depths. Students of hydraulics constantly mix these up. Alternate depths have the exact same specific energy in a theoretical, frictionless world with no jump. But we must focus entirely on conjugate depths. Why? Because across a hydraulic jump, massive amounts of energy are violently lost to turbulence. Energy is definitely not conserved. What is conserved, however, is specific momentum. Conjugate depths are the unique depths before and after the jump that share the exact same specific momentum.
Let's dig into the math in Section 4, Calculating Conjugate Depths. Because energy is violently destroyed in the jump, engineers can't just use standard Bernoulli energy equations to predict the water level. Instead, they have to turn to Newton's second law of linear momentum. As noted in the source material, the ratio of downstream depth to upstream depth is uniquely dependent on the incoming Froude number. This fact is mathematically derived as the famous Belanger equation. It proves that the height of the jump isn't just random chaos. The resulting downstream water depth is a rigid, physical response dictated entirely by the excess momentum carried by that incoming shooting flow.
If we break down the distinct classifications based on their Froude number, a really fascinating pattern emerges. If the number's too low, the jump is weak and doesn't dissipate enough energy. If it's between 2.5 and 4.5, you get an oscillating jump that pulses and creates massive destructive waves. That is a total nightmare for engineers.
Instead, look at the 4.5 to 9.0 range. Engineers specifically aim to create this steady jump. It's highly stable, it stays anchored in place, and it safely annihilates up to 70% of the kinetic energy. It is the absolute gold standard for design.
All right, Section 5, Engineering the Stilling Basin. Knowing the math is one thing, but how do we actually build a physical cage to contain this violent phenomenon? Well, we use a stilling basin. It's a paved, highly protected concrete channel section designed specifically to contain and anchor the hydraulic jump. Think of it like putting thousands of tons of screaming water into a violent timeout. By deliberately triggering the jump and forcing the water to fight a heavily reinforced concrete floor instead of the fragile natural riverbed further downstream, engineers protect the environment from being entirely swept away.
To make these basins shorter and more cost-effective, while maximizing the destruction of energy, engineers install heavy concrete accessories right in the path of the screaming water. Chute blocks are placed at the start to literally slice up the incoming high-velocity flow. Baffle piers are massive concrete blocks placed right in the middle to act as blunt impact barriers, generating intense turbulence. And finally, end sills at the very back create a subtle backwater pool that anchors the jump inside the basin and deflects the remaining flow slightly upward, which prevents ground scour.
And finally, Section 6, Taming Megawatts of Power. In practice, engineers follow a really strict blueprint to safely contain this energy. Step 1, they compute the inflow and Froude number. Step 2, they calculate the mathematical conjugate depth using the Bellinger equation we talked about. But here is the critical trick for Step 3. They must carefully match that required depth with the actual natural tailwater depth of the river. If the river isn't deep enough, the hydraulic jump won't stay in the basin, it'll just violently sweep downstream and destroy everything in its path. To prevent this, engineers will literally dig the basin deeper into the earth until the depths perfectly match, before moving to Step 4 and selecting their specialized basin type.
But listen, the engineering here must be absolutely flawless because the hazards are genuinely terrifying. When water velocities exceed 15 meters per second, the local pressure can drop so low that the water actually boils at ambient temperature, creating vapor bubbles. When these bubbles are carried downstream into higher pressure zones, they collapse. This is called cavitation, and it produces localized shock waves of over 1,000 megapascals. That is enough explosive force to literally tear high-strength concrete apart, piece by piece. So engineers have to use perfectly polished surfaces and introduce aeration slots to cushion the floor from these microscopic detonations.
To put the sheer scale of this energy into perspective, let's look at a practical calculation from our source material. For a relatively modest spillway discharging 50 cubic meters of water per second, the resulting steady hydraulic jump physically annihilates 2.39 megawatts of continuous power. Just think about that for a second. Over 2 megawatts of raw, structure-destroying kinetic energy is transformed into heat and sound over a span of just a few meters, entirely contained by a mathematically perfect concrete cage.
It really leaves you wondering, doesn't it? If a single relatively small spillway safely destroys 2.39 megawatts of power every single second, what other invisible, violent physical phenomena have engineers secretly harnessed just out of sight to protect the modern infrastructure all around us? Next time you look at a dam, you're going to know exactly what's happening beneath the whitewater. Thanks for joining me on this explainer, and keep questioning the world around you.